Oh, they gave me lights here. That will be interesting. Good evening, and thanks for coming. Can you turn it down a bit? Good. This talk is about the future. It's trying to give you some ideas what could happen next. And I see quite a few young people here, or maybe not so young. You can be the inventors of the future. In order to do that with lasers, I want to tell you a story. The story how we got to have the laser, and then we can project it from there. Now I can sort of barely see you, and I'm going to ask you some questions. I'm trying to find a good spot. That's about here. How many of you have used a laser today? Have used a laser today? About a quarter? Okay. Let's see what the answer to that is at the end of the lecture. So, where do we start the story? Well, about 100 years ago, the world looked quite different. There's a photo of Hamilton I found. There were some cars, yes, so that's not quite right. There were definitely no TVs. Was there electric street lighting? Maybe, but not much of it, if at all. Definitely no computers. So imagine such life. It's not that long ago, 4 generations, and it was very different. Already at the time, there was optics. There were optical instruments, like this microscope there. And if you want to understand that, really you only have to understand rays of light. You know, a ray like from the sun to a tree, the shadow the tree casts. That's a ray, a straight line. Also, people learned the hard way that in order to make better instruments, to see stars better or to use biology better, they had to use big lenses. Now, you might think a telescope is big because it catches a lot of light. That's correct. But also you have to make it big, otherwise you can't resolve a tiny little star. That's as important in making these really, really big telescopes. And the same applies to a microscope, which is a bit counterintuitive. You know, you might want to polish a little lens better, and then people showed, oh, a big lens works even better. So diffraction, the wave nature, became important. So what's a wave? Well, here we have a wave, and it's moving from a center. Sorry. What have we got there? Interesting. Okay, so we have a wave here. That's just one moving out from a center. And if we have 2, it's moving, yes. I have to watch that screen. Then you can see you have a reflected wave on the left-hand side. So effectively, you have 2 sources, and you get interference. So the wave can add up, or they can cancel. Good. So that was the knowledge. And the question is, what was new? And the new thing came by looking at the sun. So let's assume that's the sun. I gave you some glasses. Can you put them on, please? Now let me see. I got a little miniature sun here, and I might be able to go past you. So it's flashing up. What do you see? You see a rainbow? Right, thanks, that's very helpful. I can find some people there up there. That's just a little torch here, which is my mini sun, or you can look at the dot up in the projection screen, and you see the usual rainbow. There's red, there's yellow, there's green. The novel thing at that time was that people for the first time were actually able to measure how much red, how much yellow, how much green, how much blue. They were able to measure this with a very high precision. And that wasn't very simple because you need different type of detectors. And the first time that was possible was at the end of the 19th century. Now, once they have the data, and this was done in a lab in Berlin, they asked around whether anybody could explain that. And the theoreticians said, oh, sure, that's easy. We give you the equation, and here's the equation. If you plot it, it fits beautifully, but it had a problem here. Did anybody care? Come on, you know, a measurement somewhere in Berlin, a theory from Vienna, I mean, not more big deal. Why should you worry? This guy worried about it. Would you like him as a lecturer? Looks a little stern to me. That's young Max Planck. A sideline story is that he was told not to study physics because he was a talented person and he could play the piano, and his professors at the University of Munich came to the conclusion there was nothing new worthwhile studying. I think the world has changed a little bit. I think they want you now as a student rather than pushing you away. So he wanted to complete physics, he was interested in puzzles, and he could solve this puzzle, but he had to make an assumption which he never really enjoyed. And that is that he had to think about light being made out of little bits and pieces of energy. And he used the word quantum. So he made a new theory, a new type of statistics, and he got that curve, which sits straight on the measurements. Did anybody care? Probably not. One person did, Albert Einstein. That's more the real Albert, not the photos you see with the tongue stuck out. That's what he did when he was old. This is what he looks like when he was actually doing all these amazing things. So he got involved in this topic, and he made a new bold statement that the energy of these particles was related to the frequency of the light or the wavelength. It's a wave, so it has a wavelength. When he published that, most people were very skeptical. And they had debates like this. So here you see a group of quite active and leading physicists of the time having a debate. Einstein here, and the special one there who came specifically from across the Atlantic was Millikan, who didn't believe in Einstein's work at all. But he did the right thing. He went back and said, well, let me try to repeat the experiments. If I can repeat them in the way you say, I'm going to support it. He did. The photoelectric effect was repeated, and he became one of the biggest supporters. So there we have the photon. Now, a photon in those days was something in the mind of the people. A photon nowadays, let's see. Thank you. I got a photodetector here. It's a little bit what you have in your CCD or your smartphone. It's just been trimmed to the level that it can detect individual photons. So if we open it a little bit, you just get a few. Dark, light, lots of light. We would call that noise. So in modern technology, we can detect one photon at a time. Have you heard that sound before? Sure you have. It's normally a Geiger counter, right? A Geiger counter counts very energetic particles. The trick is, can we do this with low energy particles in much the same as our eye? Well, I would go as far and say, if you ask me what is a photon, it's a click. When I have a click, I know there's a photon. And that way it keeps me very nicely out of the other philosophical debates, what a photon might be. So now we have it, rays, waves, particles. Which one is it? Well, some people did a demonstration like a double slit here. So they put a nice laser beam through two little holes. And you can do that at home if you get one of the safe laser pointers. We talk about that. Have two little holes, and you can actually see a pattern. And that's because each hole is a wave by itself, and these add up. So as we have seen with the water waves, you know, here the waves add up, there in the middle they cancel. And people have used this effect and used the camera, our colleagues in France, and as you can see, up there, each one of these dots is one photon. Initially, it looks very chaotic, but when you wait for a while, you see something emerging. There are lines here with a lot of intensity, and the lines where it's very dark. Now down here is a counter that is basically counting in real time how many photons have been detected straight above. And as you can see, there's this modulation coming up. Bright, dark, bright, dark. The contrast is getting better and better the longer we wait. The reason why it's bright and dark is the wave effect. The way we detect it is photon by photon. These things are happening at the same time. When we think how the light got to the detector, the wave picture is very good. If we think about what happened at the detector, the photon picture is good. They're not exclusive from each other. Okay, we need all of that. So Albert Einstein continued, and then he came up with something that nobody could measure. He said, well, if I think about lights and atoms, I can think about three processes. The first one is how light disappears. There's atoms, there's photons, they get absorbed, and the energy is stuck in the atom. I can also think about how light is emitted, for example, in the sun. I have these excited atoms, and they send out a photon. The atom is quiet again. People knew all of that, but he said, in order to make my equations complete, I need a third one. I need a photon going into one of these excited atoms. That will lose its energy, and I'm going to get two photons. I couldn't say which one is which. They have completely identical properties. He said that in about 1916, and it took over 30 years for anybody to measure it. I mean, why would you believe it? Come on, you know, a guy says you need this process and nobody can see it. It might as well not be there. However, some people thought, well, that's quite cute. If I start with a lot of excited atoms here, one photon will lead to two, 2 to 4, etc., etc. There will be a whole avalanche. So what I've built here is sort of an amplifier, isn't it? I stick something small in, I get something big out. So we're cloning photons, and we make many of them, and they all have the same property. They fly in the same direction, they have the same color, same phase, anything we ask, they do the same. Now that was the status in the 1920s, 30s, 40s. And after World War II, after people were busy with all sorts of other things, physicists were pretty much in demand in those days, they came back and said, maybe we can do something about it. And here's a group of people who got really involved. Not surprisingly, it was on both sides of the Iron Curtain. This was a time when the Soviet Union and the US were competing for superiority in technology and in science. We have some engineering type people. We have experimentalists. We have more theoretical people, and they all got together. And so they cooked up one more idea. Let's say, let's combine the amplification with the interference. So if you start with a mirror here and a mirror there, and you line them up such that the light bounces forwards and backwards, and you put your excited atoms in the middle, you're going to amplify one photon into, let's say, 3. And now you arrange it that this one is a perfect mirror, and this one lets a little bit out. So one photon flies out here. The others go back, and you turn that into more, and into more. And now you see that you're setting up a fairly large wave inside, and that is sending out a stream of photons just in one direction. And that's the reason why we have a laser pointer, right? From the laser to the whiteboard is a straight line. And it's only that light that bounces many, many times forwards and backwards. What we have built, an engineer would say, we have introduced feedback. And I don't dare to do that. Put this microphone next to a speaker. You know what will happen. Ooh, big sound. That's feedback. Now this is optical feedback. And we would say that's an oscillator. So we have built a light oscillator based on stimulated emitted radiation. Problem with that, isn't it? If you read it out loudly, it sounds like a loser. So we can't have that. So we replace it with amplifier, and there it is. The first laser, so now we have it, was made 1960 by an engineer. Someone who was insisting that he had the right way, and where actually the university people were saying, no, it's not going to work like that. So he made a ruby laser. And that's what it looks like. There's a crystal in here. This is where the atoms live. He put other atoms in there. He put a flash lamp around. This is like a photographic flash. And this made the excited atoms. And then he put at either end a mirror. And part of the trick was making the mirror. Because if it loses light, this is not going to work. So ignored the ridicule of the university people, went ahead, and yes, there was a tiny little flash of light coming out. And the New York Times reported that we have this marvelous device. As they said at the time, it was a solution looking for a problem. So, the next generation, and here we have a laser from the physics department here in Otago. It's almost historical. That was about 1961. Now, if you put your glasses back on, I don't think this is 61. This is probably, what is it, mid-80s, early 90s? We don't know. So what do you see if you look at this line here? Can you see the rainbow again? Really? What do you see? Do you see different colors? But I hope you also see individual colors, right? Not just a smooth rainbow, but individual lines of different colors. So what you have in front of your eyes is a spectrograph. It resolves colors. And so these are the excited atoms. And this is actually a neon sign, right? Believe it or not. But we have mirrors right on top and at the bottom. The light is bouncing forwards and backwards, and only the red light cleans it all up, and that's why we have this red output beam. And it's exactly the direction of the two mirrors. So there we have it. The next generation of laser. So, what is it that we want to use it for? What do you think people proposed to do with a laser? Give me some ideas. Yeah, maybe medical, surgical, drilling, that's good ideas. Anything else you could do with a laser? Oh, you're really clever. This measuring distance, yes, we can do that too. Oh boy. Stocking, yeah, supermarket, bar, you know, all of them were right, but unfortunately this gentleman got it nailed. The first proposal was a death ray.
I do have a new toy, but considerably more practical. You are looking at an industrial laser, which emits an extraordinary light, not to be found in nature. It can project a spot on the moon, or at closer range, cut through solid metal. I will show you.
Well, if you want to see the rest, get the DVD. Is that real? The time is 1964, 4 years after the first laser. Is that what a laser sounds? We have this evil scientist. Do we have a real laser? Did you see how it was glowing red in mid-air? Is that true? Not really. That was painted on film, right? That was science fiction because they didn't have it. Now we got a laser, but in order to use it, I have to do a bit of safety precaution. And just to explain a little bit what you can do and what you can't do at home, there's a legal limit, a speed limit, so to speak, for laser pointers. Now, what would happen if you look into the sun in the middle of the day, blue sky, sun coming down on Hamilton, one of these great days, which we have so many of in Australia? Would that damage your eyes? Have you ever tried it? You can admit to it. Everybody tried it once. Did your eyes survive? Why? You blinked, right? Yeah, it hurts, so you know something is wrong, so you blink. So that's the same precaution for a laser pointer. It's set at roughly the same energy going through your eye as the full sunlight. It's just one color. Sunlight is all colors, but that's sort of secondary. And so they set the limit that you can blink quickly enough if it really goes all into your eye. These are the laser pointers you're allowed to buy. As a teacher, you're allowed to use in your classroom, etc., etc. Unfortunately, anything higher needs a few precautions, like glasses. So at least I'm safe now, right? So when I turn my laser on, which is about 300 suns, we can then observe what might happen, and where we can actually see the laser beam. Now so we haven't got quite a death ray, but we can certainly shoot balloons. Did you watch that quickly enough? Well, here's the slow motion of that. We turn on our laser, and it might take a little while in this case, and then you can see flying it apart. What do we actually do? We just heat rubber, right? We deposit the light energy in a tiny little point, we melt the rubber at that point, and the balloon is the rest of it. So please don't try it at home, because most likely your laser isn't above the speed limit. Okay, so death ray, yes, but what has it got to do with this? Well, if you want to make one of these cars, or actually nowadays, it doesn't matter which car you're looking at, if it's a safety car, it will use lasers for welding. So we're going to do exactly the same. It's just that this laser is more around 1 million suns. So you have to take even more precautions in your factory. And as you can see, you can make a continuous weld, and that's what you need for a safety car. So what started off as the death ray, which led President Reagan to initiate Star Wars, became a very big tool for safety science, namely making cars. And one of the gentlemen pointed out that you can do that like here with high repetition, but you can also do very fine details. So for example, here's a drill. Now that's actually a very small drill. It's only 3 hairs thick, right? But if you have a laser, that's okay. We can drill a hole in that. And it could go smaller. It goes down to a wavelength. It goes down to a micron. So we could take a human hair and do a bit of a sculpture on it, like you see up here, right? So that's what's done with a laser. Or we could do maybe some eye surgery. Now we got some eyes for you. Here's a lovely example. and something went wrong with it. Can you see that there's something growing in the eye? This can actually happen in reality, some growth in the eye. We like to remove that, so we need an expert. Can I ask Dr. Dörr, Anne? She has trained long and hard to remove things inside eyes. So here is your eye. The patient has another one, so that's okay. Need a tool. So how would you get the growth out of the eye? Poke a knife into the balloon. Seems easy. Oh, you're in. Well done. Thank you, Anna. Now, is that perfect, Anna?
It's got a hole in it.
It got a hole in it. So what are you going to do? Stick a bit of...
Fix it.
Yeah.
Fix it.
Yeah. Well, you need another surgeon, right? Okay, can we invent a technique how to do this without going a hole? Fortunately, we have another eye. Almost as beautiful, is it? Which way you want to hold this eye? Like that? Okay, I think, Anna, you might need some protection here. We're going to use our laser again. Okay. So here's my laser. Here's your eye. Not yours, but all right, the one and I turn it on. 3, 2, 1. Voila! It's gone.
No hole.
How did that work? Is the balloon intact?
No hole.
No hole. So why is that? Come on. Give me an answer. No, we didn't seal it. We didn't make a hole in the first place. The white color. There was a dark balloon. You know, we were cheating a little bit. There was a dark color inside in the white balloon. So you can imagine the light goes through. And this is exactly what you have in eye surgery. Well, actually, they were very close to each other. So the focus was about the same. Yeah, you could play a trick and focus inside. We didn't do that. We just relied. We were optimists. We relied on the fact that the white balloon would like that light through and the dark balloon would absorb it. And your trick is perfectly right. With an eye surgeon, they focus the laser in it. Thank you, Anna. We need you for... You come back for one of the... Sorry, I didn't send you off the stage. So, that's the surgery, and here's actually the slow motion, right? So 100 times slower, you see what actually happens. The light penetrates. Now you can play even more tricks with different colors. And in eye surgery, what you have is a balloon of thousands of suns, and the surgeon pushes a pedal, and it just gives a flash each. You can actually put... now, did I do that? Yes, now I probably started the video, yep. So you see there's a lot of oscillation on the outer balloon, but there is, it's unperturbed, it just vibrates, and the balloon inside is completely gone. So that's what we do in eye surgery. Now, thanks to light-emitting diodes, we have actually all these powerful lasers now. This, by the way, is the spectrum of a light-emitting diode. That's a white diode as I have it here. It's not quite what the sun is doing. You see there's a bit in the green missing, but it's good enough to give you a torch. And so thanks to that, the lasers are very small. They're actually just, the laser pointers here, the lasers is barely a millimeter big for making that light. Here, we're talking a few millimeters in that type of laser. So, Let's see, Anna. Did you move the beam dump? Do you think we hit it? I think we hit it back. So, if I turn on my laser, I want to convince you that, where's the green stuff? Where's the... Oh, you found it. Good. Can you dim the light? Let's make the light beam visible. Bit higher. Yeah. If you want to do that at home, anything, this is a room spray actually, lovely flavor. Don't use hairspray. That goes all over the furniture. But do you believe that this is a straight line? Thank you for the lights off. So, you can take the glasses off. Good. How can you bend it? How can you bend light? Would a magnet do? Gravity. So you mean the photons are dropping down? Not really. Can you use gravity to bend light? How much mass do you need? Lots, like a ton? Like 1,000 suns? One sun will do. Tiny little bend, yes. You can do some lensing, you can do that. But I would actually challenge you that light is bent by gravity. And I would say, well, you know, the whole coordinate system is bent, and the light is just following the coordinate system. The trick is you can't do both, so you have to decide. Either you say that, but then you have to keep the coordinate system intact, or you go for the coordinate system, and then the light follows it. So in a way, light is actually the definition of a straight line. Fiber optic will do it. Yes. So, Anna, can we do an experiment to bend the light? Yes, you need your glasses again. We need some water. We need a bucket. And the tricky part is that I'm supposed to leave a minimum amount of water on the floor here, they told me. So I put my finger on there. Beautiful water, New Zealand. Great stuff. So here we have another one of these lasers, a little bit above the speed limit. And let me give you water first, and then I'm trying to turn the laser on. It doesn't hit it.
Doesn't hit it.
Okay. How about there?
I think a bit more that way. Ta-da! Almost, a bit more. Bit better.
Some fun. I know what I'm doing. I'm bending the plastic. Is that better?
That's better.
Okay, I was bending the base plate. A new trick, right? Go down with the bucket. Let's see how far we can follow the light down. Yes.
I think we're losing it there.
We're losing it there? Okay. Well, that's certainly bending the light, isn't it? There we go.
Oh, it wasn't too bad.
So, what was bending the light? What was it? The water. What does the water do? Diffraction, that's a little bit too complicated. Refraction, yes. You know, if you sit in a fish pond and you have fish, what can you actually see? When you look up, can you see the sky? You see a circle of sky, that's right. If you look a little bit sideways, suddenly it stops. And all you're going to see is look back into the fish pond. You can try that one day. Dive down, look with your goggles up, and see how far you can actually look. The water is going to reflect. And so if you're surrounded by water walls in all directions, all you can do is bounce forwards and backwards. This is an experiment you can do at home, like these people here. Well, they were actually quite ambitious. They used a green and a red laser pointer and a water bottle with natural springs or something like that, and a hole on one side, and they managed to get both green and red light out of one hole. There's a challenge for you. You can try that at home. These are legal laser pointers. So, obviously you do that. Thanks, Anna. Thanks for the help. And how was the spill? Is it okay?
Oh, it's all right.
Okay. We'll mop it up later. So there's our fibers. This is what you have connecting all the major communication centers. This is what you have connecting the cities with each other. Okay? This is what connects the continents. New Zealand connected with Australia and the US via optical fibers. So how many people have used a laser today? All of you, right? You have used probably the internet. You have probably Googled something overseas or some news. You have used the information. So the communication, maybe you didn't have eye surgery today, but you certainly used the internet. So it's interesting to look at that as a historical sort of sequence. How does an idea turn into an instrument and from there into an industry? So you have atoms are particles, light is a wave. That's where we started. Lamps, telescopes, cameras, and photocopiers. Took about 20, 30, 40 years. Same with quantum materials, invented in the 1920s and 30s, eventually leading to the transistor and from there to the computer. Photons took actually a remarkably long time, as you heard today, to the laser, to welding, DVDs, medicine. And the research from the 60s is just emerging nowadays as so-called quantum technology. And we come to that in a few minutes. So maybe that's something you could tell your local member of parliament, some other decision makers. You know, be patient. Put something into science and the reward will come. But it might take 2 generations. Get more kids into schools thinking about it, and then you have the engineers and the whole society benefits. But now, let's go back to your interference, right? You know that waves who come together add up to a big wave, okay? Waves where a maximum is simultaneously, with 2 waves, one is a maximum and one is a minimum, they cancel. We can not only make mirrors, but we can make mirrors where half equal waves come out here, so half of the intensity goes there and half the intensity goes there. I think it's time for an exam question for you. You don't want an exam? This is a scientific talk, come on. So, here's an input beam. There's our beam splitter, there's one wave, there's the other wave. We bend it around the corner, we come to a second beam splitter. So far, so good? So, we could, for example, have this light reflected there and the other one coming through, and we could have everything coming out in one direction. We could have equal amounts coming out the other direction. That's another option. Or we could have all the light coming down to the bottom. So I think the way I've drawn it, option 1, everything to the bottom. Option 2, equal amounts. Option 3, everything to the right. You have compulsory voting in New Zealand? I think it's a good idea. We charge all the Aussies who didn't vote. So let's treat it as a compulsory voting. Have a talk to your neighbor. Which option do you want? Should the light come out to the bottom? Should it come out to there? Or to both? So let's see what happens. Who is for option 1, which is the light going down? Yeah, there's some brave people. Yes. Okay. Yep. Who thinks the light goes in both directions? There's more hands going up. Who thinks it should only go there? There's another group. Who didn't vote? Okay. Well, I can tell you, all who voted got it right. I didn't quite tell you enough, didn't I, for the experts? I didn't exactly say what happened at that point. Did the waves come together or did they come opposite? Actually, you only have to wiggle that by one wavelength, which is about 100 times smaller than your hair. That's a tiny little amount. And you switch from option 1 to option 3. But there's something in common. All of these are possible, because in all of these, the intensity that comes out in both of them is the same that comes in. Nothing gets lost. If I had given you one option where there would be less or more than you put in, that would be wrong. To those who didn't vote, sorry, you didn't get it right. Okay, so we have a new class of instruments, and this is a very powerful instrument. We can wiggle one of these mirrors, and it's only by a tiny little movement that you get that it switches from one output to the other. These things are called interferometers, and there's many, many applications, including measuring length, defining our length standard, and measuring all sorts of vibrations and fast effects and slow effects using an interferometer. Well, since you did so well, all of you passed the exam, I can't really find out who are the bright ones and who are not. So I give you a second question. This one only has one correct answer. So we take the same beam splitter, we put 2 photons in. You remember these photons where we couldn't say which one is which? 2 identical photons into a beam splitter. What do? Well, they could go both down, and so we have 2 photons coming out here and none in the other arm. They could go to the other side, and we have 2 there. Both of them could be reflected, so we have 1 each. Or both of them could be transmitted, and we have 1 each. Can anybody spot another option or without? 2 would energy violation. You put only 2 in, so you can only come out with 2. Can we have 1.5 and 0.5? No, it doesn't work with photons. We can't split a photon. So they have to be whole photons, and if we put 2 in, they have to be 2 out. But it was a good point, so I think we covered the possible results. So, for your voting paper, the first option, they're all possible, so they have the same probability, okay? Second option, no, you really like them to come out in pairs. You know, let's think about them very social. Individuals going in, couples coming out. Is that the behavior of photons? Or are they antisocial? Never form pairs. Now, for those of you who are physicists, quickly do the calculation. You don't need anything more than for the previous one. Same equations. Those who are not physicists, don't worry, there's only one right answer, and we actually teach it at second-year university. But have it a go anyhow. Think about it. Which one is it? Equally likely, pairs, or individuals? So let's see. Who thinks that all of them are possible? Option 1. Yes, a few people gain. Yes, good. Who thinks that they always form pairs? Who has been in my lecture this morning? Who thinks that they come out individually? Yes, right up there. So, as I said, this is not easy to guess. The purpose of asking you the question is to show you that the physics can be counterintuitive. The first answer would be pretty logical, right? And this is what you actually think about probability. They all can happen. They're all equally likely, so why don't we give it a quarter? However, if you do exactly the same mathematics as for the interference we had before, you will find that the last two results actually cancel each other. It's a weird thing that something can cancel. But in quantum mechanics, you think about a probability wave, and it can be positive, and it can be negative, and it can cancel in the same way as an electric wave, or a water wave, or an acoustic wave. And it happens to be that this is the example where these two outcomes here come out with a probability just opposite and cancel. Do you take my word for that? As David said, this guy has done some physics, he should know. Be skeptical, right? Always ask whether he can tell you how this is actually done. So this is the correct answer. We have those people who came in the morning, remembered very well, thank you. Here's the proof of the experiment. With the experiment, you start with one of these green photons, you turn it into a pair, twins, you move them on, you send them to the beam splitter, there they pass through, that's where the waves merge, they go to the detector, and the detector click, much like we had it before. The trick here is we only count when they click together. So we're counting the one-ones. If they leave in pairs, pair up there would only make one click, pair down there would only make one click, we don't count that. But 1-1, that's recorded. So there's the experiment. It was done first time 1987. The way they did it is they've sent out the photons one before the other. So they measured how many 1-1s there were. They shifted the beam splitter a tiny little bit up to they came simultaneously. And as you can see, these double clicks just vanished. Logic, they only came out in pairs. 1-1s we would have seen. There aren't any. And then they moved into the other direction, back to the 1-1s. Now, that's counterintuitive. You can't guess that. You can do the mathematics and you get it right. And it shows you one of the examples where the quantum world is slightly different. Now, people like Roy Glauber, or here's a photo of Dan Walls from about 85, who worked in Waikato. Now, Dan was a PhD student of Roy. Margaret was a PhD student of Dan. So you have 3 generations here, academically. They showed us how to measure this properly. But let's not go there too deep. Let's just think about the future, what might happen. So one of the applications is that you use the laser beam for communication. So Alice talks to Bob, and we introduce a new partner, Eve. She's the eavesdropper, but she's a very clever engineer, right? She takes things out and she puts them back. And Bob wouldn't even know. I think the NSA has worked that out quite well. Right? So unfortunately, this is happening. However, if Alice decided to use one photon at a time, we now can't split the photon. So the photon either goes to Eve, in which case Bob doesn't get anything, or it goes to Bob, in which case Eve doesn't get anything. So as you can see, they get information, but they only get sort of half the story, or they get noise. Now people have worked on that, and then came up with a protocol. So if Bob says, well, no, this is not looking good, then we do this again up till it looks fine. And after all of that, sorry, I have to go back. No, there's, oh, okay, something missing, but that's fine. You end up in a situation where Bob has everything and Eve has nothing. So that would be a true quantum technology in the future. Let me point out another thing you can do with lasers. You know, we have already very good colors. We've got red, we've got green. The attraction of the laser is that I can say exactly which red and exactly which green. I can tune it. And so, for example, I could have a chimney here, and I'm not quite sure what comes out of the chimney. Might not be good for you. Or you might want to find out what they do at night compared to day. Might be interesting. In either case, you could mount a laser and actually shine the light up and get some light coming back. So we shine it up, a bundle of photons. Ah, okay. Now, obviously, we screwed up here, but that's okay. We'll go further. Yep, so a light there. Okay. Sorry, I mixed up the slides. So light goes up, light comes back, and we can tune the color to exactly the poison we are looking for. Is it water vapor? Is it just CO2? Is it something dangerous? Is it dangerous? Is it toxic? So we can do that. This is called LiDAR, and so you can measure things at a distance. We can also make very short laser pulses. Actually, they are so short, they're the shortest thing ever reported. And Ursula Keller was one of the pioneers to make these very short pulses. They can be so short that you can actually see what is happening inside the molecule. And that's really at the limit. Finally, why should we just stop with lasers? I hope you learned something about lasers, but we could do the same with atoms. Actually, if you look closely enough, you can make an atom laser, which literally means a stream of atoms coming out, all being coherent, forming a wave, interfering, and lo and behold, there is a gravimeter. This is the machine down in Dunedin, and it works by interfering atoms. I'm sure David can tell you about it, because it comes from his research center. So this is where I finish my story, but this is where the future begins. I hope you are part of it. You see that all of these people were necessary to make the laser and to use the laser, and you can be part of the future. Come up with an idea. Tell us about it. Thank you for your attention. I hope you had some fun. I hope it was interesting. Thank you very much.
So thank you, Hans, for both a beautiful and very fascinating and informative talk. I can't see anyone to point at anyone, but I'm sure that Hans would be happy to take some questions. So.
There's a microphone coming.
So are there any questions?
Yes, there are. There we have one here to start with.
Okay, I'm sorry.
Yeah.
You almost got on to photon entanglement.
Yes.
I've been reading about entanglement and they've been spinning photons, transmitting one, and then the one that is retained, if it is inspected or something done to it, the other photon is instantly changed. Not at the speed of light, is instantly changed. That's what I keep reading. Is this correct?
Partially, I would say. So the entanglement is about the fact that when you look at one of them, you know what the other one is. However, if you wanted to check, you still have to send a message at the speed of light. So in order to test that the other particle is indeed what you think, you can't communicate faster than the speed of light. So that, while the idea is there about instantaneous, you can't use it for anything, because you would have to send the information. So there's a bit of confusion about this communication faster than the speed of light an entanglement. Entanglement is really about knowing what is at the other hand there. I would say in order to really appreciate entanglement, you first have to appreciate the statement from Roy Glauber, that there is an uncertainty principle. And where things got interesting in the old days was that people said, well, you can't have on the same time an uncertainty principle and say precisely what is there. This is contradicting. But we have resolved that by now. So we can give you special pairs of photons. We can also give you pairs of laser beams, and you can measure one, and you can predict exactly what the other one doing within all of that uncertainty. To me, that's entanglement. I hope it helps you a little bit. Right?
What do you think has prevented lasers from becoming more mainstream in areas like dentistry? I speak to my dentist every time about when she's going to get a laser, and she still believes in a drill.
Well, is it not mainstream? I mean, in many cases it's hidden. So I guess if you're interested in welding, it might not yet be the cheapest way of welding. But if you want a precision weld, something where you have a continuous weld and it's highly reliable, you would do that. If you go into the cutting industry, I don't think you even know whether they cut it with a laser or not, but they do. I mean, that goes up to shipbuilding now. So it's pretty pervasive, but it might not be the cheapest solution. In every one of your iPhones and smartphones has little bits and pieces in it that you could only make with a laser because the parts are so tiny, right? Your little accelerometer, for example, that allows you to turn your iPad around, you cannot make that. But there's no one saying made by laser. Maybe it's our fault. So I think in the special case it's actually very pervasive, but not necessarily the cheapest. Does that help you?
If there aren't any more questions, I'm just going to add a caveat to that, in that we have one of our students recently went to work for Scott Technologies installing laser guidance for the meat chain in a meat factory just in Balclutha. So they're not doing the cutting with lasers, but they're actually lining up the carcass for the meat chain. So these sorts of things are in mainstream industry, even in New Zealand.
Yeah, the barcode readers in every supermarket, right? You wouldn't even think about it anymore. And I don't think that is state-of-the-art surgery. I mean, you know, it's so common now that you have an eye surgery with a laser that you sort of, I think that's a good thing about it. Nobody talks about it. You need a laser to read and write a DVD. Nobody talks about a laser being necessary for the internet. There's more lasers being made in a quarter of a year now than there are people on Earth. Ah, that's a good one. I was following that, and the US Army is still promising Star Wars 30 years later. It's going to happen next year. Yeah, but you know, luckily it's not very good for that because the lens has to be so big. So if you have a fighter aircraft and you really want to shoot down a satellite, you need a big focusing lens. And that's one of the weaknesses. So I think nature protects us a little bit from that. Lightsabers. Well, I know about people who have such intense lasers who can make a plasma, a glowing piece of thing, a meter, 10 meters, 50 meters long. We got that. They haven't figured out what to use it for, fortunately. So Star Wars is a little off. Thanks for that.
So are there any more questions?
I've got one, I'm not sure how to frame it though. Quite interested in photogrammetry and the idea of using lasers as part of the visioning, computer visioning.
Right.
Yeah. So, what can you tell me?
Can you use your microphone so everybody can hear?
Quite interested in the idea of using lasers as part of computer vision and photogrammetry, measuring things for 3D scanning and such like.
Yeah, I mean, okay, so what's the principle of 3D scanning? You send a laser around in every direction, you pick it up very fast, and you reconstruct what the room or the object is like.
Yes.
That's possible. Why is it? Yeah, I mean, I would think it probably has a great future in exploring things where, is it better than vision? In some cases, it's more accurate, so you can measure the distance down to millimeters and measure. So I could see some numerical things in there, yes. You can do it from a robot, and I would think if in 20 years, I'm pretty sure we'll have lots of robots who are pretty smart, and they might have eyes like ours, but they might have laser beams. And certainly Google car has laser beams on the top to figure out where it's driving. So I think that it neatly fits into what you want to build. Keep on exploring, but the principle is pretty much send light out, get light back, measure how long it took and how much it is, and put that together to an image. That's roughly the principle. Unless someone has a refined version of that. Interference in there, Rhino? Oh, we get the microphone to him? That's another one coming. Rainer here, Rainer Künnemeyer from Waikato, is involved in this. Switch on.
It's on. Okay. Does it work now? There are cameras now around that work on basically laser distance measurement in 3D. You can buy them from Microsoft or similar companies, and they're used for gesture recognition. In general, mainly used for games, though.
So they pop up everywhere. My hobby in the moment is to poke around brains and see whether I can understand how neurons work. That's another long story. But basically, we can focus lasers now into brains, and maybe one day we can figure out what's actually happening there. That's pretty ambitious, but this is typically what research should be doing.
So I might take a liberty and ask one last question. But so you've told us a story about the history of the laser and lasers in technology today, but you were also director of the Centre for Atom Optics in Australia until very recently. Could you tell us, and I'm quite interested from a professional point of view in this as well, do you see something or places that we can actually go in terms of atom optics that we can't go in terms of laser science? What can we do more?
Well, I mean, I think you're on one of the most important tracks. One of the differences is that atoms actually respond to gravity. They fall. So these atom interferometers are very good to measure what we know as acceleration. So if I would walk around this stage and have a very, very precise map of how much I'm pulled down, I could actually figure out what's below me. If there was a very heavy block of iron and I walk straight over it, there would be just a little bit more pull than when I'm not there. The amount is ridiculously small, but that's what you're measuring. So we have already satellites going around the world that look at the distribution, density distribution of the air. We're exploring the world out there, and these are laser instruments. But the prediction is that if we had an atom interferometer out there, makes about 2 orders of magnitude, a factor of 100 better. Now that's a bit of a challenge. Take your lab, David, shoot it up to a satellite, keep it running. So not there yet, but that's just one example where I think atom interferometers, for example, have a big hands-down win over things that lasers can't do. And you could look behind walls, right? Couldn't you? If there's something heavily hidden in there, why don't we have a super gravity meter walking up and down there and saying what's behind the curtain? You don't have to look through, just measure gravity. It will come.
Okay, if there are no more questions on a forward-looking note, I'd just like to thank Hans once again for a visually wonderful talk and a very informative talk. So thank you very much.
Thanks, David.